We're turning movement into electricity and then putting that on a computer. So the process would be, it would look something like this. We would have a sensor worn on the body, and as the person moved, we would record the electrical energy that comes out at the end, the voltage. And typically we'll plot that on a little graph that looks like this, where you've got time along the x-axis and you've got the energy of the signal on the y-axis. So that's just a sort of very standard engineering approach for taking data and turning it into electrical signals. But to do anything useful, we want to get it on a computer. And that's where we're talking about ones and zeros. So we turn those voltage readings into numbers that are stored on a computer. And then we can do things with it. So that's a very basic primer for everyone with, who've not been doing engineering, but just curious what a sensor is. Now, one of the big issues with sensing, and it was alluded to in the last talk, is that sensors are never accurate. They're always messy. Or more to the point, even if the sensor is accurate, the world isn't accurate. The world is noisy. There's a lot of deviations from how you expect things to be. That means you can never quite trust the data completely. So we always have to factor in noise whenever we're sensing things. Let's look at one of the most common sensors that is often used in all of our research and has quite a useful application in sensing live performance. And that's when we're sensing movement using wearable sensors. Now, the most common sensor type used is an accelerometer. So accelerometer measures acceleration, which is, if you apply a force and there is a change in velocity. So a way of thinking about that, a very simple idea of an accelerometer, you can imagine you've got a tube, and there's a little picture of one here, and there's a weighted ball in that, and it's attached either end with springs. And if you just hold it still, the ball doesn't move. But if I start to move it, the ball will move again. And then if I'm moving at a constant velocity, the ball will just stay still again. So it's only measuring change, acceleration. So let's look at this example here. We've given this little man an accelerometer, a single axis, so it's only pointing in one direction, an accelerometer that points horizontally. It's pointing horizontally backwards, and we've attached it to his thigh. And we record him over time, and he's just standing there, and the signal we'd expect to see is just a straight line along zero acceleration happening. Then he starts to walk. And as he walks, the sensor moves about. His leg is moving around. And that movement can be captured with acceleration. There's these changes, the starting and stopping, the moving of his leg can be recorded like this, and it would look like a little sinusoidal wave. Then he sits down, and something interesting happens. The acceleration goes to, what is called 1g. And that 1g is one gravity. What's happening there is, the reason we're all on the ground, mostly, is that we've got gravity holding us down, and that's constant acceleration. And that's a constant 1g of acceleration forcing downwards. An accelerometer will pick that up. So if you're facing your accelerometer downwards, it's going to pick up a constant gravity, even though it's not moving. So there's going to be a constant signal here. Little man gets up again, stands, and he's not moving, and there's no gravity happening on it, so there's zero acceleration. That's the accelerometer. Usually when people talk about movement sensors, this is the sensor they're talking about. Now, very often, we're not just looking at a single axis like this, a single arrow. We're interested in 3 axes. The world is, X, Y, and Z. We've got up, down, and left and right, and so on. And most little sensor chips will be equipped with a 3-axis accelerometer. Many of them, and you'll see this in many applications too, is a thing called an IMU, or inertial measurement unit. And that records 3-axis acceleration, so X, Y, and Z, but it also captures rotation around those axes. So it's like a gyroscope. And it would also have compass points, so we're pointing north, south, east, and west. Now, with an inertial measurement unit, you can capture a lot more complex information about the orientation of the sensor in space. You can't get the exact location of it. For that, you would need to do some relative positioning using multiple other sensors. But that involves combining lots of sensors together, and that's another topic. Well, almost another topic. So connecting this a little bit towards our research, the research in my background, I've been interested in trying to use sensors to recognize regular everyday activities, so-called activity recognition. Now, this application I'm going to talk about seems a bit silly, but it's useful in many instances where we're interested in safety monitoring of people that are using power tools or repairing aircraft engines, making sure that they do it correctly. And we wanted to use an accelerometer, a 2-axis accelerometer at the time, to detect whether someone was using a saw or not, and various other tools. Now, if you can see here, you can imagine if they put the sensor on the person's wrist and they're moving it back and forward, you see this little sawtooth wave as the person saws back and forward. And there's a little bit of noise here, but you could basically get a nice signal. The problem is a computer that looks at this data, and even if you just looked at this data, you couldn't tell it was necessarily a saw as opposed to pumping your fist up at a rave or something like that. There wouldn't be, this was a long time ago, this experiment, there wouldn't be a way to differentiate it. So what you need is some additional information. Now, as humans, we've got multiple senses. So we can see something, we can smell it, we can hear it. The more modalities you use in sensing it, the higher quality, the better the accuracy of being able to recognize what it is. So if we add a microphone and record sound in addition to movement, we've got a better chance of recognizing that specific activity. That basic premise is behind the idea of multimodal sensing. And that follows into lots of other applications. So another type of sensing that we often want to do, and particularly when we're monitoring audience people who are sat still and not moving very much, is looking at their heart and recording their physiological signals, which are actually, we don't need a special device to do it, we just need a wire, because our bodies create electrical signals that we can just measure using electrodes. So for example, in this project, there was a heart monitor we built. It was a wearable heart monitor. It could record your heart signals, the electrical signals of your heart, the ECG, as well as various other physiological parameters. Unfortunately, getting those signals alone is not enough. It needs to know something about your movement. It needs to know something about your activities. So if you're monitoring someone's heart and they have a problem with their heart, how do we differentiate that problem from when they've just drank too much coffee, or they're going for a run, or they're having an argument with someone? We need to understand all the information to better process the data and to make sense of noisy data. One of the sensors that Guido Orgs has used in the past, and I've used too, and Daniel Richardson, who will be talking tomorrow, is this the Empatica wristband, which does multimodal sensing. It records electrodermal activity. It's a sweat response, if you like. It used to be called galvanic skin response. It's the thing they used to use in lie detectors. It records acceleration, 3 axes, heart rate, temperature. And here I've recorded my own data over a period of 2 hours watching a theatre performance where we were recording people in the theatre. And you can see my stress goes up through the roof at the start of the performance, but as the performance goes on, my stress goes down, the EDA goes down. There's not much movement during the performance. And so you can start to analyze data signals like this. Now the the penultimate sensor I want to talk about. So I'm going through all these sensing types very quickly here, so please, you can ask me at the end if you've got any questions about them, is the eye. The eye is the most revealing sensing modality we have in many ways. And it both signals to other people as well as receives signals. Our eyes reveal a lot about our intentions and what we're thinking. Now, there's a nice way to sense the eye. You could put cameras on the eye, and there's all sorts of camera eye trackers. I'm not going to talk about them just now. I'm going to talk about a sort of slightly less obtrusive method called electrooculography, or EOG. The eye is basically a battery. It has a voltage across it. So if you put electrodes either side of your eye and you move your eye, the voltage detected either side will change. So it's like a potentiometer or a variable resistor, if you like. Now, this approach has been used in the past. Shackle used this back in the 1960s to create this mobile wearable eye tracker. It could track the up and down movement, left and right movement of the eye, and then it correlated that with the images taken from this neat head-worn camera. More recently, we've tried to replicate this. The way in which your eye moves tells something about what it is you're doing. So we don't always need to know what it is you're looking at. We don't need to know that, oh, I'm looking at a person or I'm looking at a book. If I look at the patterns my eye makes as I do it, it can reveal a lot about what it is you're doing. The classic example is reading a book. If you're reading, your eye moves from word to word to word, then it goes to the start of a line, it starts again. So we did a study where we tried to recognize whether someone was reading or not while walking around, a challenge. We had them sitting, standing, walking, standing again, riding transport. And all the way through, we recorded the horizontal movement of their eye, little electrical signals, and the vertical movement of their eye over a period of several hours. This data was really noisy. There was a lot of interference from all the electrical lines around, the movement patterns, very hard to work with. However, if we also recorded the movement using acceleration, so movement of the person's head, there's a movement sensor on their head, accelerometer, we could discount all those instances where they were moving a lot and discount the data from that and only choose the data when it was like not a lot of movement and it was nice and clean. And we could do other sort of signal processing things. So the idea of combining different sensing modalities to improve your ability to recognize activities. And the final sensor I'm going to talk about is brain sensing, or the thing that we're going to sense. Now, the brain is, well, basically, we don't really know how to sense the brain. We can't read thoughts, where neuroscience is not as advanced as we often think it is. But we can read the symptoms of things that are going on in the brain. Now, what I mean by that is when the synapses in your brain fire, they create magnetic fields. Now, to sense those magnetic fields, you could use a thing called an MEG scanner, a magnetic encephalogram. Those are traditionally very expensive and huge, £1 million buildings, all hermetically sealed with clamps around your head, and you're unable to move. But they're pretty good if you don't have to move. It's not going to work in a theatre. This group here made a wearable version of it, but as you can see by the image, it's not incredibly wearable. It only allows you to move your head about, 10 centimeters or so, which is not ideal if we are interested in studying how someone's enjoying the theatre. This person looks very relaxed. An alternative is to look at blood flow in the brain. So if blood flows to a region in the brain, it may be indicative of brain activity of some kind and localized. And that blood flow, we could look at specifically the oxygenation or the hemoglobin or deoxygenation in parts of the brain. And we can do that using light. So if you shine a light into the brain, into the skull, the different hemoglobin levels have different refractive properties. So the light will come back to a sensor and give different readings. So basically, you're creating a whole bunch of light sensors and little lights and sticking them on your head and then sealing it so that the sunlight doesn't get in. This is the functional near infrared spectroscopy approach. And there are nice wearable solutions to that. A project that I did last year used that in a theatre. Very expensive though, and we can only really record 1 or 2 people at a time. So the solution for most cases like this, where we want to record lots of people, lots of audience members, is to look at EEG, electroencephalogram. And Guido, pictured here, is going to talk more about that with a demonstration on Friday. So I won't talk too much about that. Just going to wrap up. My background, in addition to wearable computing, is theatre. So to the side of the work we're doing in dance, and this project is centered around dance, we're also looking a little bit at theatre and what that means, to sense it and how performers connect with each other and connect with audiences. And this project called Deconstructing the Dream, which happened at the Bloomsbury Theatre, I was going to say last year, but it's now 2 years ago, pandemic. We put headbands on everyone, audience members, performers, and they had little ambient sensors. These are little IMUs, inertial measurement units, that do 9 degrees of freedom, XYZ, acceleration, gyroscope, and magnetic field. And we put them on everyone's heads. And we wanted to look at the signals that came out of them. Now, here's a very messy picture, but somewhat simplified representation of the overall head movement for each person. Each line represents a person, an audience member or an actor. Each colored line represents that. And this is over a 1 hour period, 1.5 hour period. Now, just looking at the data, you can see slight differences. You can see here, this is the actor's data. They're moving a lot in the middle, which is when they're performing. They're not really moving much either side. Whereas the audience, see all the other people, they're all moving during the interval So this was halfway through the performance, and then not moving a lot once the performance starts. Now, there was a bit where several audience members were then brought up onto stage. So they were initially audience, and then they were asked to come up and participate. And at that point, you can see their signals. So this person is a classic audience person, moving around at interval, not moving, they're sat there, and then they get up on stage and they do the same movement patterns as the actors. What I mean by showing this data is we can do all sorts of signal processing and analysis of this, but just visually, you can already see social links between all of the people in this theatrical performance. And we can start to study their behaviors without knowing who they are and without having a lot of data on them. All we've got is the movement of their head. So this social interaction using wearable sensors is very much the heart of a lot of our research. And I believe Hayley's going to talk a bit about that in the next talk. I have a lot to say about deconstructing the dream. We also did FNIR scanning of the actor's brains. It was a world first to scan an actor's brain during a mid-performance. But for now, I'm going to leave it there, and I'm going to invite, now we're going to have questions at the very end. So I'm going to invite Hayley to come and join me and take over.
Hello. Let me see. I think I just need to share my screen now.
I'll just introduce Hayley while you're sorting things up. So Hayley is an associate professor at the Socially Perceptive Computing Lab at TU, and the presentation is up and running. I'll let you take it away, Hayley.
Hi. So yeah, my name's Hayley Hung. I'm an associate professor at Delft University of Technology, and I lead the Socially Perceptive Computing Lab. So just a little bit about me. So I guess we're in the techie group today, perhaps. So my background is in electrical engineering. I did a PhD in computer vision. Perhaps what is sort of less officially known about me is that I do have quite an interest also in the arts. So back in 2010, I had an interactive arts installation, and I was interested in how there was this kind of relationship between the installation piece itself and then how people were interacting with it, and whether this could be something that was measured. As well as that, I'm also a violinist on the side, and I love improvising, and so spontaneity as a way of experiencing music and live performance is something that interests me a lot. But anyway, so in being asked to give this talk, it actually reminded me a lot of some of the interests I had in live performances in the past, because I don't really do so much of that now. And I'm showing you a picture now of a live street performance, because what I found interesting in looking at the arts and public life, or the social life of public spaces, as some call it, is this idea that people can become engaged with each other through these live performances when they might have been strangers passing each other and never interacting. And so this example, this picture here, sort of embodies that idea from a phenomenon called triangulation, where through a live performance, audience members might start kind of socially connecting with each other in ways that they might not have done otherwise. And so in my past, I have also worked a little bit on the relationship between social life and dance performances with the Holland Dance Festival, where we wanted to see if there was a way of seeing if social life could be enhanced by watching a dance performance. So they organized these events where people would actually do social networking, so kind of a mingling kind of drink session before watching a live performance, and they would watch the live performance and then they would mingle again afterwards. And so we measured people's behavior using a wearable sensor hung around the neck and an accelerometer, triaxial, as Jamie was mentioning earlier. And we measured them during the mingling, but we also found that even when people were sitting and doing almost nothing, which you also saw in Jamie's presentation earlier, those points where they just sat, the signals are very, very, very small. We actually found that we could detect if people were enjoying the performance or not, and that people tended to synchronize their behavior at moments that were, let's say, favorites of audience members. But anyway, so that was my, let's say, segue into what my main research is about, which is about measuring social experience, ultimately to enhance it. So let's start with the why. I mean, hopefully everyone would like to see social experience enhanced. The idea being that it should be improving then our social relationships, our productivity, and our well-being in general. So this is really related to the health message, which was also presented in Evelyn's talk earlier. And so in my lab, then we do a mixture of different things. There's the computer science angle, and also an engineering perspective, which is then how do we bring this technology to the real world and what are the trade-offs of that. And then also a very important component is social science. So when people are having these networking events and socializing, what type of social theories or affective theories can we bring in to help us, let's say, make an artificially intelligent perception system. And so the type of social behavior that I'm particularly interested in is shown here. Excuse me. So this is an example of the mingling behavior actually before the dance performance, but I actually have recorded multiple data in this way. And what I find particularly fascinating about these scenarios is we know very little about them, and they're very hard to measure. So, you know, if you see all of these different people moving around and talking together, making new bonds, maintaining existing social bonds, then what is it that makes us or draws us to these types of events? So in trying to measure and answer that question, then there are some really kind of neat technical challenges that from a geek perspective then make me interested in knowing more. So one of them is, well, we don't have clean sensor data, so how can we develop novel automated approaches then to handle this noisiness? We don't know actually even necessarily where the conversations are. They're dynamically changing all the time. And then this means that different people are influencing each other in different ways that are unpredicted. There's no sense that we're going to have this conversation now between this time and this time. And as well as that, it also, because it's so difficult to look at, then even social science doesn't have a rich understanding of what's going on. So that makes it kind of appealing for me. So then the way that we actually look at these kinds of situations is to measure them using sensors. So here is just a couple of different examples. They could be wearables, cameras in the environment, and also wearable microphones, for example. And so there's many different ways of doing it. Some of which Jamie already mentioned, so thanks for the intro on that. But I think what, from my perspective, then also, let's say, makes it interesting or encompasses what we're doing is that we sort of have two kind of soups going on. We've got the soup or the cloud of real-world social signals, you know, being transmitted and received. And then if we want to put this into an artificial system to perceive what's happening, then we have these sensors that then receive all of this information from the real world and then record it in all these different digital forms. And so then the big question is, well, how do we make sense of that? And so I call this bridging the semantic gap. So the main idea is that you have these signals that are recorded, and then so the signals themselves aren't necessarily already the representation of the meaning that we run, right? It's just a signal. So we need to transform this signal into meaning, the red box over here. And so what we need to do is use machine learning approaches, artificial intelligence, in order to take signals, the data, and well, actually have humans help us, help the machines learn what it is that the data should be telling us. That's not something that is let's say, an easy and direct relationship. Sensors are noisy, the representation is noisy, and the meaning sometimes is, or this truth is not always so easy to find. And so one way that we get some help rather than just stabbing around in the dark is to use social science as an inspiration for how we collect the data, how we label the data, how we model it, and how we finally interpret it. So I guess going now on to the main theme of my talk, then I mentioned this idea of studying authentic and spontaneous social interactions at fine timescales. And the important words here is authentic and spontaneous and fine timescales, because this is actually very, very hard to do. Typically, when we want to center people up, then we can do that at fine timescales in lab settings, but then it's no longer necessarily as authentic and spontaneous as you'd like, especially if you want to measure social life. And so my group has been very busy in the last 10 years or so, trying to work out, well, how do we even measure this? And then on top of that, how do we organize spontaneous and authentic situations? So here's just one example of that, which was a speed dating event, as a collaboration with social scientists, where we organized a speed dating event followed by a mingling session in order to try and get the type of data that we wanted. So again, we see now that there's this overhead camera setup similar to what I showed you earlier. Also, each of the participants was wearing a sensor that was hung around the neck that measured acceleration and also proximity to other people. And so this data was recorded with these sensors being wirelessly synchronized at the 1 second level. So that means that every second, then we know that the data is synchronized. But in reality, when we talk about, well, I guess this idea of liveness or spontaneity, then we know that it's going to be happening at much finer timescales. You know, human response times are much faster than that. For most social behavior that related to, for example, speaker changes, back channels, so, you know, saying, aha, yeah, nodding, facial and body mimicry, they occur more or less, you know, at a different time scale, sort of a maximum of 40 milliseconds latency. And so this 1 second synchronization that I mentioned is actually problematic. And so what we've been trying to do in my group in the last couple of years is to find a way of measuring behavior in authentic settings, but also then do this in a way that is allows us to investigate the dynamics of this spontaneous behavior at a more reasonable frame rate. So actually this is achievable already with wired lab settings. There are some very nice hardware solutions to this. But when it comes to the wireless setting, this becomes actually quite challenging. So you can do it, but at great expense by synchronizing with GPS satellites. But then one of the problems is it's extremely expensive, and then as researchers sometimes, or you know, performers, we don't necessarily have that kind of level of resources. So fortunately, we came up with another way of synchronizing different data, all the different data sources together, by using NTP instead of the GPS solution, which gave us something that's more cost effective, and more importantly, given the latency that we can tolerate for human response times, was actually reasonable. So we didn't need to go for the lower level latency that the GPS solution would have afforded. So this is an overview of the setup where, because I use camera networks quite a lot in my work, importantly to be able to see how people are behaving, and then to have humans be able to say, okay, this is this behavior. It's a way for us to visually verify what's happening, and also potentially to use it for our automated system. So this part is kind of quite crucial. As well as that, then to really measure more fine-grained behavior of individuals, then we also have each person wear a wearable sensor, which is then connected wirelessly. And so you can imagine now that with all of these sensors working together, then how do we bring it all together to be at a reasonable level of synchronization? So what we did was that we used this NTP representation of time in order to do that. What's very neat about this approach is that we can use commercially available hardware and to set this system up, which makes it extremely appealing then that, it's something now that we have the paper published at ACM Multimedia last year where you could take it and then build your own system. The wearable network here is just, it can be any, so as long as it can run on this particular time standard, then you will be fine to use whatever you want. So that allows you to be able to connect up the standard for audio visual, which is LTC, then with whatever wearables that you have. So aside from the synchronization part, then I just want to mention a little bit about authenticity and spontaneity, because this is very hard. So I mentioned already working with social scientists to collect data, real life speed dating data. But actually, when we want to talk about social life, then it tends to happen also in working settings as well. And if I want to now understand a bit more about the social life of people, how people are interconnected, and at a fine time scale and a fine resolution, then we need to find communities who are willing to do that as well, which can be hard in this day and age. And so 2 years ago, then we managed to work with a conference in order to do this. And the initiative was called ConfLab. And the idea was that we could integrate our measuring setup or data collection setup into the fabric of the conference itself. And at the same time, then release the data back to the community. So the idea then that the individuals are participating in the process of giving data, but this data is not active, but also captures real relationships. And so just to kind of bring us back, I showed you this diagram earlier, and what I hoped is that by being able to measure spontaneous behavior and go through this cycle, that we can also then bring some new understanding back to the social sciences, or whatever this new interdisciplinary thing would be called. And just to say also that even though I'm talking about crowds, then these research can actually be implemented in office spaces, speed dating, human-robot interaction, social surveillance, and also looking at even at dance performances as well, and all the way back up again. So just to conclude, then, enhancing social experience starts with authentic measurement. Measuring experience leads to understanding and automated interpretation, and progress in enhancing experience requires interdisciplinary collaboration. And as a final note, privacy and respectful data collection at the individual level is really needed, and I'm happy to discuss that later.
Thank you very much, Hayley. That's wonderful. I'm going to ask everyone to bank your questions in your memory or write them in the chat, and we're going to have a question session at the end. So I'm going to thank Hayley, and then we're going to move on to Kai Kunze, who is a professor at KO Graduate School of Media and Design. Take it away, Kai.
Thanks a lot, Jamie. So let me get this started. Okay, I think you should be able to see my screen now. And yeah, so my background is actually similar to Jamie, also in variable computing. However, also from my talk, I'll quickly give you an overview over the topics that I discuss, a little bit of personal background, and then I'll go from the physical activity recognition that Jamie a little bit mentioned towards more on sensing what is going on in our mind, and then looking into a little bit of augmentation, individual and also collective. My slides are online on my website, so if you just type bit.ly Liveness Kai together, you should get the slides. So about myself, although I work at the Graduate School of Media Design, I'm also completely technical. So my background is in variable computing. I'm now already 7 years or so on, however, in Japan. So first Osaka Prefecture University, and now since 5 years or so on at Keio University. And that's my research group here, quite diverse. You see also, this is in front of our house temple in Kyoto. One of my researchers is a Buddhist monk, Taka. And however, my background is actually in physical activity recognition, and I was using devices like Jamie showed, accelerometer and other things, to detect activities or context-aware systems is the topic. And the background here is just that, you know, if we have more and more sensing devices, if we have more and more computing around us, the bottleneck no longer is, you know, CPU or RAM or some other technical property, but really the bottleneck becomes human attention. And I realized that quite early. You see two pictures from my desks, one in Passau, one at Park, that, you know, kind of even if you have the best interfaces, if you have too much computing around, it's quite hard to deal with it. And I always wondered, you know, kind of how can we get computing closer to our bodies? And work we did quite early in this, and this is kind of the traditional variable computing setup from around 2000s, 2005. You see a worker at the machine at size. We detect his activities. A cabling error happens, and then you give feedback on a screen. So you know, kind of tell him, oh, something is going wrong, and you try to help him. The machine tries to help him, tries to support the work of the maintenance worker in this case. And however, over the time, I moved on from this and try to figure out, can we also understand something more that is going on in the mind? I used cognitive as a term, but might not be, you know, kind of too accurate. It's just something trying to understand internal processes of us humans with external sensors. And the first applications, the first things we did was we used eye trackers. You see here an example, optical eye trackers, but also Google Glass, tablets, smartphones, and other things to then display or to try to figure out what is happening. However, the problem there is if you're using an eye tracker, yeah, you know, kind of it just doesn't look nice. That's the first thing. I mean, now they got quite smaller and nicer. Toby is making now one that looks very similar to eyeglasses. Also, Pupil Labs and Visible have some nice devices. However, still, you usually have a battery runtime of 3 to 4 hours. You have to carry, you know, you have to have some kind of cable on you. You have to carry around a device. And so I was quite happy that I could get collaborate with Jeans glasses company here in Japan. So since the last 5 years, I worked with them on Jeans Meme, that's a smart glass. And it's not a full-fledged computing device, it's just a sensing device. It has the accelerometers that Jamie mentioned already integrated into them, also a gyroscope, so inertial motion unit, so you can detect head motion. But the interesting part is actually around the eyes. So the EOG, the electrooculography that Jamie mentioned before, is also implemented in the glasses. And instead of taping electrodes onto the eyes, we can use these 3 electrodes around the nose. So here I have a pair. So you see these 3 electrodes are used to detect a little bit of eye movement. So it's of course not an eye tracker. You just detect relative eye movement. And the principle, Jamie already also explained, your eye is a dipole, has a positive charge in front and negative in back. But, you know, kind of you can detect up and down movement and left and right movement, and also the eye blink, because in that case you have muscle activity as well of your eye is actually moving quickly up and down. And just as an example, I think I can show you a small demonstration. I hope it's good enough. So this works. So slight technical difficulties. So if I'm wearing the glasses right now and I'm adding here a graph, I hope the resolution is high enough. So you should see an eye blink. So blink, 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 just on the raw data. And also for the left and right eye movement, you can see left, right, left, right, left, right. So this is kind of the level what you can get with the glasses. The nice part is compared to an eye tracker, you know, kind of they're quite lightweight, 32 grams. The battery lasts the whole day, so you wire them up to your smartphone, Bluetooth Low Energy, and basically you have relatively cheap activity recognition, eye movement recognition with you. What we did with it, we tried to figure out something about your cognitive state, for example, the alertness. So over the day, so you might know, you know, kind of depending on which time of day it is, your cognitive performance is either relatively high or low. I mean, right now, at least in European time, we're heading towards rather low, so between 12 and 1 o'clock, you know, kind of after lunch. But okay, we have the lunch break later, so I might be still okay. For me, it's already late in the evening, so it's also lower, and you can detect this just by eye blink and other, you know, head movements and other things. So we worked on this a little bit. We used these glasses also for some subtle interactions. So you can do, it's called smooth pursuit. So you can follow a ball or something on a public display, and that can activate something on the display. We used interaction on the nose because these are electrodes. So you can also detect if the glasses or the skin underneath the nose changes. So we did kind of these type of interaction and sensing works with a couple of collaborators. I'm also working on the next version of meme, and that will actually soon come out, so in this year. So if you want to know a little bit more about this or so on, there's also time, or just also ping me later. And then one main part that I'm now also working on, moving away from the sensing, is also on the actuation. So how can we augment first the individual? Here I try to move towards integrating the device with the user. And in this case, I'm not meaning implantable, but I'm meaning something that is more than just you carry the device around, but the device becomes, so to say, an extension to your body. Really want to work on how can we bring technology closer to us and closer to our body, so it's integrated in a sense. One small example for this is we build a progress bar on the finger. So what you see here is just the 3 rings. And what you can do is they just give you pressure, and you can understand the number between 0 and 100 with around 10% error rate. So you have a small progress bar, you can touch your credit card, you already know, what your balance is and so on your finger. And it's quite subtle, and this tactile and haptic actuation gives you something that is quite special. There are a couple of other applications that we work in the lab, like soft exoskeletons that help improve your skill acquisition in percussion, Or another work, a collaboration with Inami and Minamisawa sensei, is we give you 2 additional arms and we do a remapping to your feet. And the interesting part here is you're moving your feet when you move the additional arms. And after a while, if you use this, you really feel like you have a 3rd or 4th arm. So that's the work on the individual. And now for the last bit, I want to go over or towards the collective. And this was motivated by initial work also together with Jamie, where we looked into interpersonal synchrony in conversations. So if we're talking in a live setting, so really to each other, then usually our eye blinks and head nods is synchronizing to some extent. And that's something that's well known in psychology. And the studies also, some colleagues here did some studies in this. And we just replicated that with the eyeglasses. But moving on from there, we wanted to see, kind of, can we also augment the collective experiments? And this is work with Mademoiselle Cinema here in Tokyo, as well as Embodied Media and Kota Minamisawa's group. In this case, really, this was a contemporary dance performance. We worked with them for now 3 years together. And first, the initial ideas where we wanted to combine perception and motion together. So what you saw with the EOG glasses and so on. However, due to also, issues with the pandemic and other things, and also the availability of the smart glasses, we recorded a small data set that's also already online that you can download and play with. So 10 or 15 people in a pre-recorded or in a performance. However, we moved then to a wristband approach. We used a heart rate and galvanic skin response integrated in a wristband that we built ourselves, because we wanted to stream all of the audience data, not just from 5 or 6 or 10 people. And we did this, and then based on the heart rate and galvanic skin response, we would change the projections on the wall, the lighting, and also the sound, so that then the dancers can actually interact with this data. To give you a better feeling on how this worked, I'll show you a video, and I hope now the sound works. So you can see each of the performers, each of the audience members actually was wearing the sensing equipment, and this was then live streamed on the screen. So you see also a debug screen, and then this influenced the music as well as the audio and the lighting of the piece. I hope the sound worked. So takeaway, we actually have the data set of 3 performances. We also have a couple of the wristbands still. We're working on the next version. Yeah, there's some insights at the end. Still a special thanks to everybody involved, because that was a large contribution, and all of the students as well. Yeah, that's it from my side. Thanks a lot for your attention.
Thank you very much, Kai. That was awesome. We have a bit of time left for some questions, and you know, we may go into the lunch break a little bit with some questions, but please, I'm going to invite Hayley back, and your daughter's there, Hayley. What's her name?
Isabel.
Hi, Isabel. Oh.
Say hello.
If anyone has any questions, please fire them away in the chat for Kai and Hayley and even myself. While we're waiting, I want to raise something about something you said, Hayley, that all of this work, part of your aim is to improve social relationships. I'd like to hear more about that.
Yeah, so I guess I take a kind of calm technology perspective on this, in the sense that it's I want to improve things, but not necessarily in an in-your-face way. So I think that the comment earlier about, well, you know, is there still space to feel pain and stuff, is also very important. And so I think there's a role for technology to have in the background, and providing, you know, sensitive moments to give you reflective ways to reflect about yourself and your experiences. So I mean, I don't have a solution for this, but let's say that this is the way that I see it, and it also then comes back to, you know, giving data. It's not just about, you know, even though I talked about, oh yeah, we just sense everything and there's this soup and everything. I mean, there's also the sense that we have to participate in that and want to get something back. And so in that more, let's say, empowered version, then the technologies also have to be something that will help us in the right way, and not disengage us by just being too attention grabbing all the time. Yeah.
But sometimes that attention can be the thing that engages us weirdly. Actually, throwing that off to Kai as well, because if we're creating performances, how do we know the performances are going to be better? Are we improving performances by augmenting these technologies?
Yeah, and I mean, not only performances, but I think that's something that I'm generally struggling with. You know, kind of, does technology improve our life or not? I mean, there's this question of, you know, you saw maybe the early pictures of me running around with a lot of, you know, kind of gear, head-mounted display and other things. And I was really expecting when I started my PhD that everybody would have a head-mounted display and, you know, a belt-integrated computer at the time, because we didn't have smartphones. And I think it's similar, I think also in terms of performance. It's always, what do you want to get out of it? And I think I still struggle, even though a computer scientist, I still struggle with this. How can we integrate computing in a way that it's not hindering ourselves, and that it's really supporting what we want to do? Because analog technologies, you know, you're wearing some, you know, glasses. That's why I actually also like the meme in terms of analogy, you know, kind of, there are some analog technologies that are really useful to us, but in a digital way, I always feel it always gets in the way, you know, kind of also the zoom. Now, I didn't know, you know, kind of, did you see the video in a way that I expected you to see it, you know, with the streaming, with the lag and so on. And it's always a struggle. So yeah, that's a hard question, but I hope we can get the answer here also in HCI and in the tangible interaction side, and really on the human factor side, because we really have to work on the interfaces. I think that's also why I feel this project is actually so cool, because I think we can learn a lot from theater and from stage performance, actually, for us, for the technology side.
We have some questions building up now, and I'm going to deal with them, not in order, but we will deal with all the questions, because I want one directly here for Hayley from Baja. How well do you think we can acquire motion information from processing videos with computer vision technologies without using wearables?
Yeah, absolutely. Definitely. I've done work in this area where we were looking at predicting attraction during speed dates by just looking at very simply tracked information. And I think that motion information is actually key. I mean, I use wearable accelerometers just because it provides some level of privacy, because we don't necessarily always need to use the cameras for processing the data. Well, as in for automated processing, but at the same time, then yeah, motion is key, and I know motion is also very important in dance. And I think that, you know, because motion tells us about our level of arousal, and that tells us about basically what we find interesting. And so for me, finding ways to capture movement in various different sensor forms, and then interpreting it is actually sort of a big theme of the work that I'm doing.
This follows slightly on, I mean, somewhat segue onto a question from Claire Van Rijn. I'm wondering about the impact that the relative social deprivation of the past year might have had on latency in human social and physiological reaction and subsequent digital detection. Also, what consideration is given to the variation in standardized social latency, e.g. different cognitive processing speeds for neurodiverse versus neurotypical individuals? Right, there's two questions there, but one of them I think follows on a little bit from the video, because if we're processing video, in a way we're all processing video now because we're all online doing our social interactions. So is that changing us cognitively? What our expectations are? Are we bringing the computer latency into our humanity, if you like?
I would say it's not just latency. I think going back to the importance of the eye, I think we're also losing a lot there. So yeah, I mean, I know that time here is very important, but I think this social connection comes a lot from eye contact. And so without that, and especially when you get into multi-party settings like what we have here, I can't tell who's looking at whom, and you know, who's making side glances at whom. All of that is now lost.
And we don't know whose phone. So I'm going to interject there. Kai, do you want to say something on that particular issue as well? Because obviously we never know all the social context when we're online.
Yeah, social context, but also on the level of especially neurodiverse or also accessibility issues. What I often heard now is that at least for conferences now, it seems a lot of people, we had the Augmented Humans 2 or 3 weeks ago, and there were actually 3 presenters with other accessibility issues, and they all said, oh, it's actually a good time for them because they can attend the conferences, but it's more, you know, kind of wheelchair and other issues that you have to cater to. For others, I think for blind or for other types of neurodiverse or neuroatypical individuals, it might be very, very hard. So it's hard to judge. I feel, you know, kind of to some extent, if we have also later on, if it goes open and we still enable streaming and we still enable the access to, you know, live captions and other things, I think that's a really nice way of interacting or dealing with that situation. However, I still feel, yeah, it's just really straining. I think everybody of us has that problem that, you know, kind of you're never sure, you know, how many people are listening or not listening. You know, sometimes you have 2 or 3 calls going on at the same time and so on. So I feel it's tricky to answer.
It would be, we're going to have a bigger discussion session later on today, and it'd be really great if people could bank some of these questions and we can reuse them in discussion, because I think there's a lot in here. I have a lot to say on neurodiversity too, because of but remind me about that later. Maybe one last question here, because we had one that was the last video of audience response has been measured and fed to performers. This is from Darren Nixon. And this seems like you're almost mechanizing the relationship between audience and performer. So you're injecting computing in between the audience and performers. So what would you say about that? Did you get feedback from the performers about
yeah, of course.
Process?
Yeah, this was a co-design process. So this was not just us coming in and trying to stick sensing on the audience or so on, but actually we work with the audience. It's a small group in Tokyo as well. So in that case, actually the dancers approached us to help, and they wanted to see how they can actually use this data to interact while dancing with it. So we had a couple of test runs or so on, and also try to figure out what makes sense in terms of changing the audio, in changing the projection or so on. If you're interested in the co-design process that was just published at TEI, at the Tangible Embodied Interaction Conference. So I agree, kind of actually also with the first impressions that we went into the, into the project, it changed dramatically when we got the first feedback from the dancers. We also wanted to put sensing on the dancers. Even accelerometers were actually too difficult. For the first performance we had that, but it was just not possible to integrate that. And, video or other tracking also did not work. So, it was a long process. And the nice thing also now is what we have the recordings of the 3 performances, and going back, we see this link between physiology of the audience members to the choreography. And that's actually something that I'm very excited about, that, talking with the choreographer and seeing the co-design process, we see that now in the data later as well. So there's this feedback loop, but there's this later data analysis.
I'm going to leave the final 2 questions for typing, and/or we'll try to reply to them maybe in the break if you're still around. But I know that Hayley has to leave us shortly. Hayley, have you got any final words anything you wanted to say?
Well, I'm going to get buzzed at some point and then have to go and help my husband with a vomit-covered baby. But in the meantime, yeah, I mean, the physiological linkage thing has been shown in media setting, when people are watching videos and then measuring physiological signals of people, and then seeing same physiological responses. I'm actually, I would be very, very interested to see how that works then with the performers as well. So I think mostly it's been done only with audience members. And I saw, just using accelerometers also, that we saw evidence also for this physiological linkage without measuring the physiology itself. So I find that quite interesting.
Yeah, certainly movement synchrony between performers is something we can certainly capture and have done, but the physiological, because they're moving so much, the physiological data is noisy. I think we have to, I'm trying to keep to schedule here, and so this session is finished. Guido, do you want to take it? Thank you very much again to Hayley and to Kai.